All right, welcome everyone to Math 20C, our third semester calculus course here at MPC, our multivariable calculus. Okay, we deal with some vector and vector notation, integrals over vectors, derivatives of vectors. Okay, we'll do that work this semester as well, right? Mainly leading into a lot of work with derivatives, and integrals with multivariables over our three-dimensional space, right? So as we begin, as you'll have to kind of bear with me as well, progress along as I do, getting used to graphing a little bit, visualizing in 3 dimensions. Hopefully with our first 2 semesters of calculus, 20A and 20B, right? The work in graphing our functions, f of x, in just 2 space, x and y axes, right? We've become a little bit more comfortable managing those. But definitely as we start to get into 3 dimensions, it becomes a little bit more difficult. But the calculation side of it will hopefully be straightforward enough. It's going to be the work in graphing, visualizing. It might take some students, myself included, a little bit longer to dive into, right? So let me go ahead and start to share my screen here, or my document camera. So if you've taken a class with me before, and kind of give insight into what steps and actions I'm taking, okay? And I'll post these notes on the Canvas website along with the recording of this video on our Canvas modules as we progress this semester, okay? And they'll be available all semester for your review. All right, so here we go. Let's get into it. I know we haven't done much of an introduction to myself, but of course, as the semester goes along, you'll definitely learn a lot more about me, and I hope to learn about you as well, okay, as we embark on this journey together. All right, so Math 20C, we're going to start in chapter 12 of the text, right? And that's dealing with vectors and the geometry of space, okay? Getting used to some of the different coordinate systems, possibly that we'll get used to dealing with, okay? But as we start to get used to this, right, we'll talk about our 2-dimensional space. Oh, sorry, this is 12.1. This introduction to these spaces, right, our 3-dimensional coordinate spaces, coordinate systems. All right. The Cartesian or rectangular coordinate system first. But in 2 dimensions, in 2D, all right, some of this notation here, we know we have our 2 axes, the x and y, right? Our 2 coordinate axes, these 2 number lines that we intersect at a right angle, right? Gives our origin 0, 0. And we can locate other positions, other locations in that space with those ordered pairs, okay? And so we'd have our point x comma y that we can identify. Okay, you have to forgive me. I don't know why writing's a little bit sloppy right now. It's been a couple weeks since I've written, taking that semester break, right? But in this case, with these 2 coordinate axes, we have our point, our position. Another name we give this 2-dimensional system, we call it R2, okay? Like a little exponent. But we call this, right, R2. Okay. Just because we have 2 real number lines being used. All right. So then, of course, now in 3 dimensions, right? And again, not to make this too boring or too simplistic as we can, but just making sure we're all on the same page with notation and discussion, okay, how I'm using these phrases, how you might see me write or in the textbook write, just to be clear there, okay? So in 3 dimensions, right, of course, now we're going to have 3 coordinate axes. And with the orientation, we're going to start to see the following, okay? So I'm going to start off with kind of like this slant. This is coming out towards us from the paper. There's my x-axis. Still horizontally across, right? Kind of going across the page. There's our y-axis. And so as we start to think about this orientation, we're kind of imagining twisting that to our regular xy plane down to be flat with the paper. And as we start to look at this orientation, we have positive x's coming out towards us, negative x protruding back behind us, behind that paper, okay? For the y coordinates, positive to the right, negative to the left, okay? And when we talk about our right-hand rule, okay, the direction, the orientation of our coordinate system, right, this kind of positive direction, I'm gonna let my fingers from my right hand point towards my x-axis. Then we curl our fingertips towards our secondary coordinate axis, the y-axis, its positive side. And then our thumb is going to point us in the direction of z, the positive direction of z, right? And so for those students taking or that have taken the Physics 3 series, Physics 3B, 3C, 3B in particular, I believe, you start to get introduced to that right-hand rule and even that 3-dimensional coordinate system, okay? So with that idea, and again, this is going to be, at least on my minor textbook here, page 832, this is the third edition, that third part of our 8th edition of Stewart with calculus, okay, 8th edition there, with early transcendentals, right? Page 832, they talk about that right-hand rule you'll see here with that orientation, okay? And so just getting used to that, it just helps us identify that as we start to go through. And again, we're going to intersect these number lines, these coordinate axes through one single point, right? The origin, now a ordered triple, x, y, z. But now when we're looking at this, we're going to have our positives going upwards, negative downward along that z-axis. And again, with paper, I know it's a little bit difficult to look at, but with online work, we can probably look to some of our graphing sites, GeoGebra, or now my mind's going blank, but the other common graphing website, okay? My mind drawing a blank, I'll definitely put it online later, okay? But definitely we have some of those graphing tools that even do 3 dimensions to get a better visualization. It just takes some time to identify how we type, how we kind of input those functions, of course, but getting used to that work. And so depending on where we are, we can identify a particular point in this space as x, y, z. And we'll later start to imagine, we start to get into vectors and whatnot. We imagine kind of like, okay, pointing out to that point, starting from the origin, using like a ruler, your pen, my finger in this case, right? And pointing out towards where that location is, whether it be kind of out towards us, back into the paper, on the left side, right, we can start to get that orientation. And again, that's one of the drawbacks of dealing with this on the dot cam, getting those aspects drawn in a little bit troublesome, okay? But getting used to working with these 3-dimensional coordinate system, the Cartesian, right, that rectangular coordinate system. Here, before I forget, right, we're going to call this R3. Okay? Since there's 3 number lines, we'll call it R3. Okay, and so we'll talk about in later work how we kind of take a three-dimensional figure and kind of project it down. Imagine if I flatten it into just 2D, R2, 2 space, okay? We'll imagine that. I don't know, kind of casting the shadow down into these different regions, all right? And so within those corner systems, right, with R2, with our two-dimensional coordinate system, we can talk about our 4 different quadrants, right? Now, in 3 dimensions, we can start to separate our different spacing, our locations, okay? And so here we have different coordinate planes. We can work in or on amongst our coordinate system, right? And so these are just different ways of organizing. I'm going to use the textbook again. I'm going to draw it. But we can start to identify, and again, this is on that page 832, right? We have our X, Y, Z axis, the positive portions, okay? So looking at it, kind of like a room, a classroom, my office, a room in your home, whatever it might be, imagining we have these different walls, these different coordinate planes that these axes separate, okay? And so we can look at the XY plane, that's the base, the floor, right? When we're kind of used to working with in 2 dimensions, the XY plane. All those points, the X and Y can tell us those locations. But Z here would be the same. Then we can deal with like the XZ plane, that left wall, this side, all those locations where X and Z can tell us our value, but Y being fixed. And then the YZ plane, this back wall, the right wall, they call it here. Thinking about those spaces, okay? So I'm going to kind of redraw this here. So if we have just the positive portions, right, we can imagine extending these infinitely long in any direction. But we can start to look at these different planes, right? So here, the one like we're most commonly used to, here's our X, Y plane. That bottom portion where X and Y can identify. Then we have over here the X, Z plane, right? Where X and Z start to separate. And then finally, this kind of like back wall, I called it the Y, Z plane, right? Just going in alphabetical order in terms of my labeling. But we're going to start talking about when we have these 3-dimensional figures, these shapes, these surfaces that are going to flow through 3 dimensions. We might look to see, well, how is that surface, how is that shape going to intersect a particular plane? Okay, so when that X equals 0, okay, what does it look like with just Y and Z are taking control? Or if I let Z equal 0, I'm on the ground level, what does that base, right, the foundation of that shape look like? How is that surface going to kind of cascade and fall and cross that XY plane? And then similar with the XZ plane. Okay. Pardon me. And lastly, we're going to start to identify as well. We have our quadrants, our 4 different spaces in 2D in R2, right? We have our 4 quadrants. Now in 3 dimensions, thinking about those spaces, how we're going to have, right, the positive side of the X, Y, Z axes, but also negative Y, negative X, negative Z. In this case, thinking about those different organizations, when X can be positive, when Y can be positive, right? Both X and Y positives and z positive, we're going to start to see we have 8 octants, right? 4 up top where z is positive, 4 down below when z is negative. We have these different octants, as we call it, these different spaces, right? So this is what we're going to call here the first octant. Right? X, Y, Z are all positive. And off the top, I can't remember how the organization goes in terms of how we start to label this as 1, of course, the first octant. And I'm guessing we probably progress that kind of counterclockwise. Octant 2 would be where the Y is positive, X is negative, Z positive still. Octant 3 back here where X and Y are both negative, Z positive. Octant 4, X positive, Y negative, Z positive, right? And then working our way down. But again, I have to double check to see how that orients. But there will be problems in the future talking about, okay, let's consider this figure, the shape, enclosed in the first octant. And that just means when all the X and Y and Z are staying positive, okay? But getting used to that location may take some time. And in the book, they do some decent pictures, okay, of visualizing these locations, how we can work our way out. But that will take some time, okay? All right. So with that said, right, that introduction to our three-dimensional coordinate system, and these notes will be scanned and uploaded to our Canvas site for review, okay? But now, what if we consider different graphs or figures, right, curves in R3, right? Later we'll start to build up into functions of 3 variables, right? But let's think about some of these types of functions, right? So for example, right, in 2D, in R2, that line y equals 2, right? That's going to be a horizontal line, right? A constant function. X could be anything. Any value you choose for X would work. But that Y value is fixed. It's constant. It's always 2. But now what about in R3? What's that going to look like in R3? Well, now, as we start to think about labeling, okay, I know my scale might be a little bit off, but we start to think about graphing here. We talked about it up top, right? X can be anything, any value. Y is always that quantity 2. But what about in R3? What about that function, that equation y equals 3 here? Okay. So in this case, again, y is, oh, sorry, I should have said 2, sorry. But we'll do 3, it's fine. Y is always 3. But it doesn't give us any mention of what x and z need to do. So in this case, x and z can be anything, any value. So we could start off by plotting points, right? We could start off, well, okay, I can let y equal 3. But in this case, the x is 0, z is 0. So that point would be 0, 3, 0, x 0, y is 3, z is 0. But maybe we'll start to march up. We can start to do this point up here. X is still 0. I'm staying flat with that xz plane. Y is 3, z is 1. Right, and we can start to progress up that direction. Or maybe I'll let z stay 0, and I'll come out to this point. This point here, x is 2 now, right, lining up. Y is 3, but z is 0. And I don't want to get too distracted or muddled up, right, make my graph too congested. But we can imagine, like, just taking all these points. I'm keeping my y where it is, but x, z, I can go wherever I need to, and it still satisfies, okay? So in this case, what we start to see in our 3 dimensions, again, I'll make it kind of solid here, but when we start to identify encompassing all these points, what we're going to see, we get an entire plane in 3 dimensions, right? This entire sheet of paper, this entire sheet of glass, whatever you kind of imagine, right? With y always 3. Okay, and again, you can imagine with a constant z value, this kind of roof to a building, a constant x, the flooring, right? Kind of think about the building aspect of it. Okay, but now starting to kind of expand our understanding or our thinking about what some of these equations look like. Okay, and then one last example I'll get into, and we'll have plenty more time to do our graphing for sure. Okay, let's consider this set of equations, this set of criteria. We have x squared plus y squared less than or equal to 4, and z is equal to 3, right? So suppose we have this, I'll put that little brace around it, kind of identify this is all together as something we might want to graph, right? And so as we start to picture this, we start to imagine, well, this kind of reminds me x squared plus y squared equals 4, which is a circle, center at the origin, with radius 2, right? The square root of 4, we get 2. Okay, and then now having it be an inequality, right? The equals 4 exactly the radius, right? So this is going to be, right, equals, that means our boundary. The inequality means all points, right, less than inside. If we had switched it to be greater than, that means we want to be outside that circle. Okay. So starting to put some of those pieces, the mathematical symbols, meanings together. And then in this case, right, with z equals 3, that height, location, is always at that z equals 3. Okay, and again, that could be anywhere. Could have been any value. But with that said, as we start to incorporate our work in graphing, and we can do the negative side as well. But what we're going to start to identify, right, we're going to make sure that all of our points stay at z equals positive 3. So we're going to be up in this region, in line, level with that z equals 3. x squared plus y squared less than or equal to 4. Well, the equals 4 part makes our boundary, right? That circle, radius 2. Dotted line just means we're back behind the axis, okay? The y and x together, producing that circle. Z equals 3 keeps it kind of flat at that stage. And then that less than or equal to inequality makes us kind of imagine filling in. So we're going to have, in the end, we're going to get this kind of disk, right, with radius 2 at that z equals 3 level, I'll call it. All right, so we have this kind of hovering disk above that xy plane. And there's some graphs and whatnot in the textbook that can also help you identify. Right, but again, we'll have more time and other common graphs that we'll work with, formats for equations, but just getting us started in thinking about how these equations and that coordinate system start to grow and kind of work to produce these graphs. Okay? All right. So with that said, just to kind of finish out with some of these ideas, these topics in 12.1. Okay? So a little out of order, but let's think about, right, this equation for a sphere in R3. Right? We talked about it just a moment ago, the equation for a circle, that x squared plus y squared equals r squared, right? Or more generically, x minus h squared plus y minus k squared equals that r squared, right? So if we just imagine expanding that, now that we have 3 dimensions, right? Now we have to incorporate that z. So just is kind of extending from what we would expect and kind of grow from in 2D, R2, we have our x minus h squared plus y minus k squared, right? So there's 2 dimensions, equation for a circle, center at hk. But now that we have 3 dimensions, now we need a z minus, I'll use L, my script L, make it not look like a 1 or something like that, squared is equal to that same r squared. Even though in 3 dimensions, we're not cubing it, it's still going to be r squared, the value, the length of the radius squared, okay? So in this case, we have our center at that location, h, k, l, and our radius, r, right? The square root of that r squared. And I'm not going to kind of do too much work today with that. Just wanting to introduce it, okay? And so we can rewrite an equation for a sphere in that standard form using that kind of completing the square process. Okay. And so for examples of this, kind of looking in the book, on page 837 in my textbook at least, right? Problems number 17 through 20. They do some work in rewriting, for example, in number 18, which maybe in our next discussion we can go through, or maybe I'll do this on the side and submit, right? Rewrite the equation for the sphere in standard form, right? In this kind of factored form, if they had given you here x squared plus y squared plus z squared, plus 8x minus 6y plus 2z plus 17 equals 0, right? Moving this up. How can we get from this into a case of x minus h squared plus y minus k squared plus z minus l squared equaling r squared, right? How can we get to that? And that's through completing the square, grouping your x's, your y's, your z's together, figuring out what we need to add to produce that perfect square trinomial, adding to both sides of the equation, right? And rewriting. But we can leave that for another day. But starting to see some of these equations that we'll see and manage and deal with, okay? The equation for a sphere. And hopefully that's a quick extension from our equation for a circle that you would have worked with plenty of times, hopefully, fingers crossed, right? Up to this point. And so now, last bit, our distance formula in 3D. Okay. Our distance formula in R3. In R2, right, is fairly quick to remember. Our distance, the square root, x2 minus x1 squared, make sure you get my ordering right, plus y2 minus y1 squared, right? The sum of those differences squared. That's going to give us our distance, pardon me, between any 2 points. In two-dimensional space, right? That distance. So now with R3, imagining that work, and again, the textbook has a better image for review. We're just going to extend that calculation, right? X2 minus x1 squared, how far we're going in the x direction, plus y2 minus y1 squared, how far we're going into the y direction, how that y value is changing, right? Still that kind of Pythagorean theorem at play here. But now, because there's also going to be a z component to it, that change, that difference in z coordinates, that quantity squared. Okay? And so when we start to look at that, okay, depending where we are, we can have our first point, P1 at x1, y1, z1, okay? Our second point, P sub 2, x2, y2, z2, okay? So now these are just labels for our points, P and Q if you want, point A, point B, and then our distance between the two. And again, the book has a kind of a nice diagram thinking about, right, how the x values are going to come out, the y value is changing, and then the z, we can start to formulate that picture. And maybe I'll try to draw that in. I don't want to get it too confused at the moment. Okay. But very similar to our two-dimensional Pythagorean theorem, now it's kind of this overlapping, this interplay between those quantities built into 3 dimensions. Okay. And so this distance, right, that's going to be the same thing as having, we'll use these kind of absolute value bars, and we'll label this together, okay? And we'll start to see this notation a little bit more as kind of a vector notation later. The distance between these 2 points, right? Distance between the points P1 and P2. or the magnitude of that segment, right? The length of that segment connecting P1 and point 2. Right, starting to bring in some of the notation as well as the language, that magnitude, that distance, that length of that segment. And we'll see some more of this discussion, this notation, this visualization. We start talking about vectors as well in the coming sections. Okay, but I'll leave it at that for now. This nice introduction to three-dimensional space, getting us used to working with some of these formulas and maybe even a little bit of the graphing part of it. Okay, all right, so these notes, this recorded lecture is going to be provided on your Canvas site all semester for you to review. If you have any questions, definitely take that time to ask. Don't let it sit too long because we are going to be moving forward, and I don't want to kind of have any confusion, limit you, kind of be a detriment to your future understanding. Okay, so if you have any questions, concerns, troubles, please let me know. Email me, send me a message through the Canvas inbox, right? Leave me a voicemail on the phone, whatever you need to do to make sure we are on the same page and understanding here, okay? All right, I'm gonna stop sharing, stop recording, but thank you. Let me know if you have any questions and see you soon.